All right, guys, help me out. What's the antiderivative here?
X cubed plus X.
Yeah, 3 just goes back up.
Plus X.
Plus X, I like it.
Plus C.
Well, remember, so these are what's called definite integrals. Because there's limits, there's numbers that tell me how far I want to go. If those weren't there, that's what's called an indefinite integral, and then I have to put the plus c, because then there's not two sides that have the c cancel. Otherwise, I don't need it. Now, if you want to put it there just to always be careful, I understand, but don't. See how understanding I am? I understand, don't do it. So now you just got to plug 3 in.
32.
27 plus 3. Minus, plug a -1 in. -1 minus 1. And you get 32. I'm like, sorry. You're good. I was just like, that's a problem. I'm like, oh, good, he's going all the way to the end. Okay, it's no problem. Alright. Nice, right? I mean, that's nice. I enjoy it. The whole reason I did so much with the antiderivatives is the more you understand derivatives and how they can become antiderivatives, the easier this kind of process is. And the easier it will be to learn integrals rules, because I hope you realize these functions we're using have all been nice. They've been nice functions. So once they aren't so nice, we have to develop rules, if we can, about how to do the integration. This guy is definitely nice.
Tan theta.
Tan theta. 0 to pi over 4. Tangent of pi over 4 is 1. Tangent of 0 is 0. 1. It's kind of neat. The area under secant squared from 0 to pi over 4 is exactly 1. It's kind of neat. So this guy...
1/3 e.
Good. So there's a 3 there. If you thought the answer was this, you know you're wrong. Basically, if you take the derivative, if it's 3 times that, the integral's got to be the opposite of that. That divided by 3. And it kills the 3 that would come down. I like looking at it like that. I need that over 3 to kill that 3. No, die. Trying to escape. Whatever.
It's places the lotion in the basket.
Oh, no.
Let's get back to math.
We still know. No fava beans. None of that stuff. So what I get here, I get e to the 3 ln 3 over 3, a lot of 3's, and then I get minus
e 3 over 2 over 3.
I like it. So you can do this, you can bring the 3 up, so e to the ln of 27 is just 27, right? That goes back up, we've seen these kind of problems. 3 cubed is 27, so I get 27 over 3 minus 8 over 3.
Or 6.33. Yeah, 6.33.
I like it. How are you doing? Alright? Good? No? Yes? So please, you know me. If I give you this kind of angle with trig, don't be giving me no decimals. Right? I know this came out to be 1. That's nice, but you know I'm going to give you some 8. Don't give me decimals with that. That screws you over. The last test on that Newton's method problem. If you would have just left the pi in there, a lot of you guys went to decimals and your answer was thrown off because of that, because you have to round when you go to decimals. I like it. So if you're in doubt, keep everything non-decimal until the very end, and then you can do whatever you want to with it. As long as you show me the answer and the exact answer. I don't care how you approximate it after that. Okay, cool. So what about this guy?
-1/3 cubed plus
3 and 3.
Yeah, I always get somebody tell me that this is x cubed. And why would they think that? They think the 3 goes up. But where would x have come from? X squared. The coefficient, the number doesn't tell me shit. In fact, I don't even care about the number. I just make sure it's there if it needs to be there, but it doesn't affect what I'm doing. It's x. It would have come from x squared over 2. I like it. So it's
3x squared plus 4x.
plus 4x from 0 to 3. And again, I was telling somebody, John, maybe, when you integrate a polynomial, if 0 is one of the limit, you're like, oh, sweet, don't have to worry about it. Be careful now, if it's e and there's 0, it's going to be 1. Oh shit, you got. Don't forget that. When you throw a 3 in there, that's going to be the answer.
8.5.
Okay, sure. Let's just run. Is that what everybody got? 8.5?
16.
16? Let's see, you get, yeah, screw it, I'll believe it.
16.5.
16? 12. Yeah, it should be point something, right? 16 minus 9 plus 3.5. 16.5?
Yeah.
Sure. Always? And then this guy, now, this just reminds you that now one little thing I want to show you. Constants, they so don't bother me that I can take them out of an integral anytime I want to. Those are the exact same thing. The area under 2x is twice the area under 1x. That only makes sense. If I raise it up by a factor of 2, of course this area is going to be twice as big. So a constant can just come out. And remember, what are integrals based on? Sums. So I can just factor the freaking GCF of 2 out all day long. Why can't I take the x out then?
What?
Why can't I take an x out?
No, that's
Function.
That's the function. That's dx. Holy shit, can't take it outside the integral. The integral's got to attack it, right? Alright, so then what's the integral of 1 over x? ln of absolute value of x. And that's what makes this possible. So then you get 2 ln 1 minus 2 ln 4.
0 minus 0 4.
Yep. So you can write that as ln negative ln 16 if you want to. Is everybody cool with that? Where'd 16 come from?
Property.
Yeah, you can even write as ln of 1 over 16 if you want to. You're crazy. You can bring the 2 back up on the 4, make it 4 squared, right? That old property of logarithms. Or if you don't want to, it's cool.
Where's the 2 before the ln? 2 ln 1.
Well, what's ln
Same
1?
thing.
0.
0. Cool. So that whole thing goes to 0. Kick your ass. Alright, so what about this? You guys are all excited. You're like, we're done with this. Handout. Leave. No. Let's see. You can do it, John.
What section is this?
Sure. It's still the same section. There's actually a little part of the homework that asks you, what's wrong with this? And they give you an answer, and there can't be an answer to this. Why not?
There's something wrong there.
There's something wrong with this, fundamental. If I wasn't careful here, I could have had a big problem. If I didn't stop at -1, I went to +1. Maybe this is easier to see, I don't know. If I had this, what is the problem? The function. Is it cool over this interval?
No, because it is
No, it sucks at
a 0.
0. Right? So, this function, whatever the function is inside, has to be continuous on A to B.
If you plug in a 0.
Yeah, do you -5 to 0 and then 0 to 2?
No, you can't even do that. Can't even do that because it goes to what at 0? Infinity. I like it. Cool. So this integral can't be done. So there are some functions that I think I showed you this. If I had a piecewise function, that I can break it up as the integral from 0 to a. It's not continuous at a, but it doesn't go to infinity. So therefore, I can break it up and actually, because this still has an area. This is just a big rectangle. This is a small rectangle. Ooh, it's still an area. It's still fine. But if I have a function that does this,
I'll never read it.
then I want the integral. I want the area under the curve.
Never read it.
Ain't no such thing.
Isn't that function also imaginary at the negative values?
No, this one no. Well, yeah, at 4 through, yeah, you're right. 4 through it's bad. That's another reason. It's going past the domain of the function. Thank you. I made it worse than I wanted to.
No.
What was the one I wanted to say? Shoot. Oh, what's interesting is something we'll learn later is if I integrate, let's just do part of it, 1 over x squared from like 1 to infinity. So imagine that. So I'm going from 1 to infinity, right? So this area, so what I'm really asking for is the area forever. So what do you think the answer should be? but it's not. It ain't. Let me give you a quick example of why. You ready? So let's say I start with 0.1. And then I add 0.01, and then I add 0.001, and then I add 0.0001, and I do that forever to infinity. Is that going to sum up to infinity?
No.
Hell no. In fact, it's going to sum up to 1/9. Right? It's going to be 0.11111. Do you understand this?
Yeah.
Do you understand this? This is huge. Especially if we're going to count 2. This kind of idea is going to drive you insane. But this, it's built on this. If the function gets out of its own way fast enough. See how it gets out of its own way? It's in the next place. The next one. It's not going to sum up to infinity. So this integral, when we talk about infinite integrals, which is just going to involve limits, not going to be that big of a deal. We can actually do that. In fact, what is the integral of 1 over x squared?
1 over x? Negative.
Negative. There it is.
Negative.
So it'll be negative x, negative 1, right? From 1 to infinity. I can't plug infinity in, but I can do a limit. What's the limit as this goes to infinity? If I try to plug in infinity, I got to do a limit. 1 over x as x goes to infinity is 0. So I get 0. Minus negative. When you put a 1 in, you get 1.
Oh my gosh.
Shit! Alright, that's just neat, right? I mean, you gotta agree with me. That's just freaking neat.
What's like the proof for like if you add like 1 plus
Oh.
a half plus a quarter plus a...
That's what this is kind of leading towards. And Calc 2 analyzes those sequences specifically. Integrals kind of are a way of testing a series out, but you have to have rules that deal with just the series. Because if I was dealing with just certain parts of this thing, like at 1, at 2, I would just be dealing with 1, 1/4, make it 1/4, Jeff. 1/8, what was it, squared? Yeah, 1/4, 1/9, 1/16. Kind of with me? I would just be adding those up. But this integral, it adds up everything, all of the values, right? So an integral gives you kind of like an overestimate of the series, what it would sum to. Anyway, that's it. Okay, so that was section 5.3. And maybe a little bit of 5.4.
Snuck it in there.
Okay.